Chapter 4, Section 4.2. Logarithmic functions. The objectives include changing from logarithmic form to exponential form and vice versa, evaluating logarithms, using basic properties of logarithms. We will also look at their graph and discuss the characteristics of the graph, such as domain, range, the types of asymptotes that they may have. We'll evaluate and look at the difference between the natural log and the common logarithm. Let's take a look at how they are defined. Definition of a logarithmic function. For x greater than 0 and b greater than 0 and b not 1, y equals log base b of x is equivalent to the expression b to the y equals x. Okay, that's a mouthful right there. Now take a look at this. We have a relationship. We know this is our exponential function. This is an alternate way to write the exponential function. So let's take a look at this a little more carefully. We have y in the logarithmic form, which becomes the exponent here in the exponential form. The base here of the logarithm is b, and that is the base here in the exponential form. And the number that you take the logarithm of is over here in the logarithmic form. So we could write this in words and say in the logarithmic form you have exponent equal to logarithm. Then we have a base down here, and then we take the logarithm of a number. So this is a way to use words instead of symbols. This is the logarithmic form. The exponential form says we take the base, raise it to the exponent, and then that forms the number. So the relationships here are that these are inverse functions, and one is simply the inverse of the other. But this is a good way to take a look at the difference between the log form and the exponential form and use the words instead of the letters. Now, just like in the exponential case that b can't be 1 because 1 to any power is 1, we also restrict here the definition of logarithm to be b not 1. And in the exponential case, this base has to be positive, and we also restrict that as well in the logarithmic form. So the function y equals log base b of x is called the logarithmic function with base b. Okay, so let's take a look at how to convert from one to the other. When you write the expression 3 equals log base 7 of x, this is exactly equivalent to the base of the log is the base of the exponential. Notice that. So first I write the base down. What a logarithm is equal to, this is the exponent. Notice the exponent right there. And then the number must go here. So log base 7 of x equals 3 means 7 to the third power is equal to x. In a similar way, this means b to the second power equals 25. This means 4 raised to the power y equals 26. So we're converting from one form to the other by using our definition here that we had before, or if you wish, the definition that we have right up here. Let's take a look at the reverse of example 1. Example 2. Now we have the exponential form here, and we wish to put this in its equivalent logarithmic form. Okay, notice the base of the exponential is 2, the base of the log is 2. The exponent here, 5, that's what a logarithm is. A very simple definition of logarithm is that it is an exponent. So the logarithm is equal to that exponent. Then, of course, the x must go here. It's the only other place where it can be. Okay, so b is the base here in this example of the exponential. It's also the base of the logarithm. The exponent here, 3, that's what the log is equal to, so the 27 is the number you take the logarithm of. This is an e-exponential, doesn't change anything. Base of the exponential, it's still the base of the log. The exponent here is still what the logarithm is equal to, and this number is what you take the logarithm of. So whether it is base e or any other base, the conversion in either direction is the same. Example 3. Evaluate log base 36 of 6. Okay, let's see. Log base 36 of the number 6. So this equals something, and we have to figure out what that means. Okay, so what we do is we convert to exponential form. So the base 36 to what power, because this is the exponent, it's what the logarithm is equal to, equals the number 6. Okay, well that may or may not be very clear to you. It turns out square root of 36 we know is 6. Okay, well the square root means 1/2 power. 36 to the 1/2 power is 6. So really this is a rule of exponents that by definition the square root of x is equal to x to the power 1/2. And that's how we obtained here in the PowerPoint slide that x would be 1/2. So that is the power that you would have to raise 36 to get 6. Let's take a look at another example. Here we have some properties. Log base b of the number b is 1. Yes, because b raised to the first power would give you b. Therefore, log base b of b is 1. Log base b of 1 is 0. Why is that true? Because b to the 0 power, by definition, using rules of exponents, is equal to 1. So yes, these are called properties, but if you just understand basically converting these to exponential form, they make perfect sense, and there's really nothing there to memorize as a property. You just note that, yes, that's a statement of the obvious. Example 4, evaluate log base 9 of 9. Okay, so this is a very specific example where the base and the number are identical. That means 9 to what power would be 9? Well, 1. So the log base b of 9 would be 1. Okay, evaluate. Let's suppose we tried log base e of e. So this is equal to something, right? So this would mean e to what power is equal to itself? Well, 1, right? So log base e of e is still 1. So it doesn't matter what the base is. What we're saying is the logarithm with any base b, and if you take the logarithm of a number that's also the same as the base b, you get always 1 for any value of b. So here's a specific example here, and here's a specific example where the b is 9. Let's take a look at a few properties that look fairly strange. Inverse property of logarithms. Okay, well, for b greater than 0 and b not 1, yes, always with logarithms, that must be the case. Log base b of b to the x is equal to x. Okay, why is that true? Well, you can see that it's true because b to the x would be equal to b to the x. In other words, I just converted to exponential form. The base to the exponent must be equal to the number. The base is b, the exponent's x, so b to the x, must equal the number, which is also b to the x. So it's somewhat a statement of the obvious there. It doesn't appear to be anything magical, but it actually comes up quite a bit in mathematics. This is another inverse property. It's not used all the time. And it says b raised to the exponent of log base b of x is also x. Yes, in a way, log base b and exponentiation with base b are inverses, so they cancel each other out, and you just get value of x there. That's not a derivation. It's a rather poor explanation of why it's true. But these inverse properties, they come up once in a while, so you want to familiarize yourself with them as much as you can. Let's take a look at some graphical work. Here's an example. Let's graph y equals 3 to the x, which we did in section 4.1, and g of x log base 3 of x. So these are inverse functions right here. Graph them in the same rectangular coordinate system. Okay. Well, we know a little bit about inverse functions, and we know a lot about what the graph of 3 to the x looks like. Y equals 3 to the x, we know what its graph looks like. Increasing exponential, asymptotic to the x-axis here, and it increases. And boy, does it increase quickly. And it goes through 0, 1. Let's put another point or two on the graph here. So we'll have a point over here. Let's say that that's negative 1. So negative 1, which we did before, 3 to the power negative 1 is 1/3. Okay, so that gives us another point there, which is negative 1, 1/3. And let's put another point on the graph here. Let's say that's positive 1. And from our previous work, 3 to the first power is 3. So this is the point 1, 3. Okay. Now, since y equals 3 to the x and log base 3 of x are inverse functions, we know that inverse functions are reflections, mirror images, about the line y equals x. So we have to fold the paper right across the dotted line, and its mirror image will appear over here. Or we could simply reverse the coordinates. So instead of 0, 1 being the y-intercept for 3 to the x, we reverse those coordinates, and now 1, 0 will be the coordinate on the log function. 1, 3 is the ordered pair on the exponential function. Reverse those ordered pairs, and 3, 1 will be the ordered pair on the logarithmic function. And then negative 1, 1/3 becomes 1/3 negative 1. So 1/3 is right here, and negative 1's down there. Now also, we have asymptote here. For the exponential function. Well, since the domain and the range are interchanged, in other words, the x becomes the y and the y becomes the x, for the log function, the asymptote becomes the y-axis. So the graph looks like this. So instead of it being asymptotic to the x-axis, it's asymptotic to the y-axis. Instead of the y-intercept being 0, 1, we now have an x-intercept of 1, 0. Instead of the point 1, 3 being on the exponential, it's now the point 3, 1 being the logarithmic function. And, of course, the A graph is not exactly to scale, but the distance away from the line y equal x to the point is the same distance away from the line y equal x to the exponential function. So this distance right here would be the same as this distance right here. And that's why it makes it a mirror image. You literally fold the paper right across that horizontal line right there. Okay, let's take a look. Yes, this is what we're doing in the PowerPoint slide. So we are making ordered pairs for 3 to the x, and then we are reversing those ordered pairs to have log base 3 of x, and then we are going to put both in the same coordinate system, and there we go. And that's a much better drawn graph. Right here is the line y equal x. Perfect 45-degree line. And yes, the blue graph, the logarithm, is the mirror image of the red graph, the exponential function. And you can see the points here very clearly. Let's look at some characteristics of the logarithmic function, I believe most of which we have already discussed. Let's take a look at them. Okay. The domain of the log function, all positive real numbers 0 to infinity. Remember that the domain and the range are interchanged, right? So it's helpful if we also have, at the same time, a graph here to look at. So we've got b to the x here, log base b of x here. Okay, so the range here of b to the x greater than 0 becomes the domain of the log function x greater than 0. Okay, the graph of the log function passes through the point 1, 0. Yes, because the inverse of the exponential function, which is 0, 1, interchanges the x and y coordinate and becomes 1, 0. Or you could also say when x is 1, log base b of 1 is 0 by the log property, because only b raised to the exponent of 0 would give you the value of 1. Okay, what else do we have? If b is greater than 0, the graph goes up to the right and is an increasing function. Yes. So this is one specific log function that goes along with increasing exponentials. This is an increasing logarithm. If we had a decreasing exponential, then we have a decreasing logarithm. I'm not going to draw that one. You can look on the textbook there for that. Since we have an asymptote here on the x-axis and x becomes y, where the domain and range are interchanged, now we have an asymptote here. So, yes. Now notice in the graph of the log, we know that log of 1 is 0, and that's for any base b. We know that. We also